Compiler, a map of the territory. First, let me establish a shorthand. Much of this course is about language implementation, which is distinct from the language itself in some sort of platonic ideal form. Things like stack, bytecode, and recursive descents are nuts and bolts one particular implementation might use. From the user's perspective, as long as the resulting contraction faithfully follows the language specification, it's all implementation details. So the language itself is really a tool for you to be able to control the hardware using a user space programming language. It doesn't matter what implementation details under hood it used, whether it used stock, bytecode, or recursive descent. So for this compiler course, we will discuss, we will create our own language. So basically, since this is huge undertakings, we're gonna do a baby step. We're gonna start with the most basic, easiest compiler we can do. That at the same time will help us understand, or will help us gain an understanding with the interesting technicalities on how the programming language actually works. The parts of a language. Though the area explored by language designers is vast, the trails they've carved through it are few. Not every language takes the exam takes the exact same path. Some takes a shortcut or two, but otherwise they are reassuringly similar. From Rear Admiral Grace Hopper's first COBOL compiler all the way to some hot new transpiled JavaScript language whose documentation consists entirely of a single poorly edited README in a Git repository somewhere. So, though not everything would have the same implementation, their path is almost the same. So there are certainly dead ones as well. Dead ends, like sad little cul-de-sacs of CS papers with zero citations and now forgotten optimization that only made sense when memory was measured in individual bytes. So just like with any other concepts, there's things or there's path that actually made or still relevant today. So it's kind of like the classics. So those are the few paths that the language designer found to be effective. But there are also some that leads to what do you say? It leads to it fade. It only makes sense that time because of the specific constraints like memory. So another lesson there is that you should choose things, a basic principle, learn basic principle that you know that will still be relevant um, in the future. So I visualize the network of paths an implementation may choose as climbing a mountain. You start off at the bottom with the program as a raw source text, literally just strings of characters. So these strings of characters is actually how we scan first the programming language. So we check that since we are the one creating the rules for our language, we know what to reference to. So basically, depending on our language, first we need to create that, and then we need to know the pros and cons. Kind of like how engineers today still do it, even with AI. They are thinking about the and cons of their decisions, and then they are still able to create an application with AI because the weigh the pros and cons. It's the same with compiler. Before you create a language, you need to know every decision why you choose that so that you can explain it. You can't just like provide the rules and then just do it. And then based on that reference, we will gonna scan that as a raw text. So we're gonna prepare for all the scenario in order for that end goal or language we want or we decided early on, kind of like beginning with the end, is actually what will show or what will be executed later on. Now each pieces analyze the program and transform it to some higher level representation where the semantics, what the author wants the computer to do, become apparent. So we start with the characters. Basically, the program will only know the characters, like the little pieces, and then it will create that, it will parse that into a tree to make sense of it. Kind of like with words, if it's a lot of words that is disconnected, it's hard to like make sense. But if it's formed into a sentence, paragraph, in a book, now you get the, one meaning or one point that the author trying to pertain. Eventually, we reach the peak. We have a bird's eye view of the user's program and can see what their code means. We begin our descent down the other side of the mountain. We transform the highest level representation down to successively lower level forms to get closer and closer to something we know how to make the CPU actually execute. So here, as you can see, we start with scanning and then tokens. So we get the tokens. So the tokens are really here. Here, we're actually scanning a token here. So we create a class for that, and then we measure the length, the argument. We read it. We do error handling, and then here is the token type. So after we create the token type, this is what we're gonna consume: package, token type, string, object, int, etc. And then this is our scanner. So we will discuss that moving forward, but this is useful. It's a baby step. This is what allows us to understand this complex material. So again, we transform the highest level representation down to successively lower level forms to get closer and closer. So here, let's trace through each of those trails and points of interest. Our journey begins on the left with the bare text of the user's source code. So the source code, like the open source code, where you can really see in your computer, unlike with a compiled program, how the program actually works, because you can delete something, you can run it again, etc. Now here, as you can see, we're scanning through this var equal average mean plus max slash 2. So that's the first concept that we were traversed. And then scanning, we'll start with scanning at the front end. There's also a front end and back end of a compiler. The first step is scanning, also known as lexing, or if you're trying to impress someone, lexical analysis. A scanner or lexer takes in the linear stream of characters. So the scanner, the one that we saw earlier, which is a class, really just a class that uses a token type, are taking a linear streams of characters. So it's consuming a character until the end. So this character will then be chunked into a series of something more akin to words. just what I said. In programming language, if each of these words is called a token. So the token that we see earlier, or that we created in we have left paren, etc. So those token here, this is the token. Um, Here token.java, so that is the words that we're gonna consume using our scanner. So as you can see, it's interconnected. Another thing is that the characters will then be chunked into a series of something more akin to words. Some tokens are single characters like open parentheses and comma. Others may be several characters long like numbers 1, 2, 3. String literals high and identifiers mean. So here mean. Lexical comes from the Greek root lex, meaning word. So lexical meaning really means just word. So we're trying to make sense of the word. Now the scanner usually discards this. Sorry. Some characters in a source file don't actually mean anything. White space is often insignificant, and comments, by definitions, are ignored by the language. The scanner usually discards this, leaving a clean sequence of meaningful tokens. So another concept in programming language is that for the source file, the usual or the proven pattern is that the programming language will not take meaning on the white space or comments, because that's are not supposed to be interpreted. Now we get into the parsing part after the token. The next step is parsing. This is where a syntax gets a grammar. The ability to compose larger expressions and statements out of smaller parts. So this is really how you create the tree, kind of like with language where you have the root and then subroot. So like here, and then from there make meaning out of it. So a parser takes the flat sequence of tokens and builds a tree structure that mirrors the nested nature of the grammar. So that's huge. Like this sentence, just like with the scanner, is huge because this parser takes the flat sequence of tokens that we got from the words. So this token actually are just a lexeme. So first, the scanner makes it easy for us to create a lexeme. So that lexeme will have the token, and that token has an ID. It has like another metadata for it to track it, but there's a lot of implementation details on that. That's why it's huge. So this takes that lexeme, or inside that lexeme there's a tokens or words, and build a tree structure. So this is another huge implementation that we're gonna do to be able to create that tree and make meaning. Kind of like a person yeah a child or kid how to like read a sentence, how to read a paragraph, how to read a book, and build this tree structure that mirrors the nested nature of the grammar. These trees have a couple of different names: parse tree or abstract syntax tree, depending on how close to the syntactic structure of the source language they are. So here is the example. That's what we saw earlier in the mountain. Many of the techniques used today to parse programming language were originally conceived to parse human language by AI researchers who were trying to get computers to talk to us. It turns out human languages were too messy for the rigid grammars those parsers could handle. So before AI, these are actually used to parse human, but because like human language are too messy, therefore this that parser that was invented by AI actually has been used in compiler. So there's already AI before this AI thing happening. It's actually happening in programming language. So first, was able to parse this easier language compared to the messy one, which is human. So, but they were perfect fit for the simpler artificial grammars of programming languages. Alas, we flawed humans still manage to use those simple grammars incorrectly. So the parser's job also includes letting us know when we do by reporting syntax errors. So in Scanner, later, we will carve out some of our code to prepare for the error so that the user know where they made a mistake.